Hello, and welcome to another video discussing engineering thermodynamics. Today I'm going to talk about the second law of thermodynamics, starting with some introduction. Then I'll talk about the concept of heat engines, then the concept of refrigeration and heat pumps. Then I'll introduce the concepts of reversibility and irreversibility. And then I'll end the video with the introduction of Carnot Cycle and principle. So from experience, we know that certain processes happen in certain directions. Like when you have a cup of coffee and the coffee is hot, let's say it's 55 degrees Celsius, and the ambient air around is, let's say, 20 degrees Celsius. From experience, we know that this coffee loses heat to the ambient air and during the process cools down. So the temperature of the coffee cools down to about 20 degrees if we leave the coffee in the open for a long time. So this is a process that we are very comfortable with. We always see that heat goes from the higher temperature to the lower temperature. What about the opposite process? Let's say I have this cup of coffee. Again, this time it's at 25 degrees Celsius, and the ambient air is again 20 degrees Celsius. Is it possible for this cup of coffee to gain heat from the ambient air and have a rise in temperature? Is it possible? Now, based on experience, we know that this process can never happen. Heat can never flow from lower temperature to higher temperature. So this never happens. Now imagine a system like this. We have water inside, and the temperature of the water is equal to the temperature of the surrounding area. Okay, so initially, temperature of the water is equal to the surroundings, right? Now, let's assume that there is a fan inside this system that is connected to a power source, and it's doing some work. Now, what happens? Now, because of the first law, we know that the internal energy of our system rises because of the input work. Increase in internal energy means increase in temperature. Now, because the temperature of the water in our system is larger than the temperature of the surroundings, heat starts to get out of the system, right? Heat starts to flow out. Now, if we let the system to reach a steady state, from the first law again, we know that all the work coming in goes into the Q. We can convert all of the work coming into a system into heat. Let me write that down here. Okay, so this is the same system. Now we want to check the opposite. So I'm going to start to heat the water inside. Okay. Again, the temperature inside the water starts to rise because the internal energy of the system is rising. The question is, based on your experience, can we just heat the water up and the hot water start to turn the fan and generate work? The answer is no. We cannot put a paddle wheel inside water, heat it up, and expect to generate electricity. This process of heating up water and extracting electricity is not in violation of the first law. So what's the problem? Why the process happens in the direction of turning 100% of work to heat, but not the reverse? Why can't we convert heat into work? Now, to answer that question, we need the second law of thermodynamics. But before we can get into the definition of the second law, we need to first start with some basics. Let's start with thermal energy reservoirs. Now, in thermo, we sometimes deal with systems that are so large in thermal capacity that during the process, their temperatures do not change. Let me give you an example. Now, this is the cup of coffee that we talked about earlier, and its temperature is 50 degrees Celsius, and the kitchen air has a temperature of 25 degrees Celsius. Okay. Now, this cup of coffee over time loses amount of heat to the kitchen air, and its temperature drops to 25. But the temperature of air in the kitchen really doesn't change. So although some heat has been transferred from the coffee to kitchen air, we know that the temperature of air in the kitchen does not rise. So kitchen air is a thermal energy reservoir, or just simply a reservoir for the cup of coffee. Another example is an internal combustion engine inside a car. So this is the engine inside your car, and it's dumping the heat into the atmosphere, right? Again, we know that the temperature of the atmosphere is not changing because of this Q. The heat capacity of atmosphere is so large that introducing some Q from a car's internal combustion engine will not change the temperature. So atmosphere is a reservoir for our system, which is our car engine. Now, usually in thermal reservoirs are things like rivers, lakes, atmosphere, and such. But you need to pay attention to the fact that a reservoir does not really need to be huge in mass, like rivers, lakes, and atmosphere. It can be only relatively large to the system that we're talking about. Example is the cup of coffee and the kitchen air. Now, kitchen air is a reservoir for a cup of coffee. So in short, a body with a relatively high thermal energy capacity that can supply or absorb heat from our system and doesn't have any temperature changes is a thermal energy reservoir. Okay, now if a reservoir is supplying heat, we call it a heat source, and if it's absorbing heat, we call it a heat sink. Okay, let's move on to the next topic, heat engines. Now, based on the examples that I gave at the beginning of the video, we know that we can easily convert 100% of work into heat, but we cannot convert 100% of heat to work as easily. Now, as a matter of fact, we cannot convert 100% of Q to work, but I'm going to talk about that in a few minutes. But there are mechanisms and machines that can convert some of heat into useful work. Now, we call these machines heat engines. So heat engines basically are devices that convert a portion of heat to work. Now, to name a few of these heat engines, we can consider internal combustion engines, where the heat from the burning of gas inside the engine is turned into shaft work that drives the car, and steam power plants, where the heat from burning fuel is converted into electric power. Now, although these devices, these heat engines, are very different from each other, but they still have 4 common characteristics. I'm gonna write them down here. Now, first, these devices always receive heat from a high temperature source. The second characterization is that they can only convert part of this heat to work. Number 3, they reject or dump the remaining heat into a low temperature sink. And the fourth and final point is that they always work on a cycle. Now, in my opinion, this one is the most important feature or characteristic of heat engines. They have to work on a cycle so that they can produce useful work on a steady rate. So this is a schematic of a heat engine. This is the high temperature source. This is the low temperature sink. And this is our heat engine in the middle. It's absorbing heat from the source. We call it Q in, while rejecting some heat into the sink, Q out. And in the meantime, it's producing a net work. So this is a schematic of a heat engine. I can give you an example in the form of a power plant. So this is the cycle of a power plant. We have a boiler. Then we have the turbine. Then we have the condenser. Finally, we have the pump. Now, boiler is where the combustion happens. So water, the working fluid of our heat engine, receives heat here. So this is where Q in comes in. Turbine is the power producing component in this cycle. So we are producing work here. I'm going to show it with W out. Condenser is where the water loses or rejects the remaining heat into a cold sink. It can be an atmosphere, it could be a river, it could be a nearby lake. This is where we dump the remaining heat from the boiler. So this is where Q out comes in. Pump is the power consuming component in this cycle. So we need to provide some sort of work into the pump for it to work. All right, so we know that the net work out of this steam power plant is W of the turbine, W out, minus the W needed to run the pump, W in. Now, first law analysis of a heat engine shows that Q in minus Q out minus W net is 0. Now, the reason that the right-hand side of the energy analysis is 0 is because the heat engine works on a cycle, and cycles are steady-state operations. So this gives us W net is Q in minus Q out. Now, with that in mind, we can introduce a new parameter called thermal efficiency. Now, thermal efficiency is the net work that we get out of our heat engine over the heat input. Now, I can play with this equation and get that Q in minus Q out over the total heat input is Q in, right? So the efficiency is Q in minus Q out over Q in. And we can manipulate this equation a bit further and get 1 minus Q out over Q in. Now, what about Q out? We are talking about heat engines. And because of the way that we define the heat engines, knowing that they are always rejecting some heat into a low temperature sink, we know that Q out is always greater than 0. It's always a positive number. We are always rejecting some heat into a heat sink. Because of that, the thermal efficiency is always smaller than 1. Now, please pay attention that the thermal efficiency represents how well a heat engine can convert heat into work. Okay, it's not a measure for how well the device is running mechanically. It's not related to friction or how optimized the system is. It is about how well our heat engine can convert heat into work, right? And the reason that this thermal efficiency is lower than 1 is it has nothing to do with imperfections or friction or anything like that. It is smaller than 1 because the nature of a heat engine does not allow to convert all of the heat into work. Okay, so again, if we take a look at how we illustrate heat engines, then this is a source with a high temperature TH. This is our sink, the low temperature TL, and this is our heat engine. Our heat engine absorbs heat from the source. I'm going to change the notation to make things easier to deal with. Instead of Qin, I'm going to call it QH, or the heat from the high temperature source. And we reject heat into the sink. Instead of Q out, I'm going to call it QL. And the W net is still W net. So the efficiency, the thermal efficiency, is 1 minus QL over QH. W net is also QH minus QL. This is not something new. I just changed the notation from in to H and from out to L. So earlier I talked about how QL is always a positive number, and as a result, thermal efficiency is always lesser than 1. Now it brings us to this question. Why do we need QL? Why the system has to reject some heat into a lower temperature sink? Can't we just save the QL and have a thermal efficiency of 1? Now the answer to that question is no. Now I can give you an example and show you why the answer is no. I'll explain in the next page. Now imagine that we have a piston cylinder like this. We have a payload on top of our piston and we want to raise it to a certain elevation so we can remove it. The system initially has a temperature of 30 degrees Celsius and it's initially in contact with a high temperature source. Let's say it's 100 degrees Celsius. Heat flows from this source to our system for a total amount of 100 kilojoules. Okay, so our system reaches the second state, where the piston has risen, the payload is in the elevation that we want, the temperature of the system has also risen to 90 degrees Celsius. Now, only 20 kilojoules of the energy provided was needed to raise the payload. The rest, the 80 kilojoules remaining, was used to increase the temperature and internal energy of our system. So this is the network, 20 kilojoules. In order for our system to be able to operate on a cycle, we needed to reach its initial state. We needed to go back to the initial state at which the system was 30 degrees Celsius, so we can put another payload and the cycle continues. The thing is, if we want to save QL, if we want to save the remaining 80 kilojoules energy, we have to dump it or reject it back into our initial source, right? But that is impossible because the temperature of our system is 90 degrees, whereas the temperature of the initial heat source is 100 degrees Celsius. And we know that heat does not flow from a lower temperature to a higher temperature medium. So we cannot reject the unused heat back into our initial source. What we can do, however, is introduce a low temperature sink, something like this, and then we can dump the remaining 80 kilojoules into our sink so that our system gets back to its initial state As you can see, there is no way that we could have saved the QL. So this brings us to our first interpretation of the second law. We call it the Kelven-Plank statement. So the Kelven-Plank statement says that it is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work. So something like this, where we have a source only, we get QH and produce W net. So this is impossible. We have to have some sort of heat rejection for a device that works on a cycle and produces work. Okay, so this statement kind of states that the thermal efficiency, as we discussed earlier, is always smaller than 1, because there is no way that we have a system that converts 100% of heat into work. So that brings us to another type of devices. These are called refrigerators and heat pumps. Now, one of the first examples that I gave in this video was that heat transfer only happens from high temperature medium to a lower temperature medium. If you want to achieve the opposite, gaining heat from a lower temperature and dumping it into a higher temperature medium, we need a device called a refrigerator. So if I want to give you a schematic of a refrigerator, here is our low temperature refrigerated area inside your kitchen fridge. This is the high temperature surroundings, maybe the kitchen air, and this is your refrigerator. So a refrigerator consumes work, receives Q from the low temperature source, and dumps the heat into a high temperature sink. I'm going to present you the schematic of a refrigeration cycle that your kitchen refrigerator is working on. So here's the evaporator. The refrigerant enters the evaporator. Then it goes into a compressor. Then goes to a condenser. The fourth component of a refrigeration cycle is a throttling valve. Now, if you remember, a throttling valve is a device that drops the pressure and temperature of the fluid while keeping the enthalpy constant. Okay, so in this cycle, the evaporator is the fridge compartment. So this is the refrigerator compartment. And the condenser is the kitchen air. And here, compressor is where your refrigerator is consuming work. Okay, so just to recap, in nature, the heat transfer process happens in the direction of heat flowing from a high temperature medium to a lower temperature medium. Now, in a refrigerator, we are doing the reverse. We are taking the heat from a low temperature medium and we're dumping it in a high temperature medium. In order to achieve that, we need some sort of a device, a machine, we call it a refrigerator, where it consumes work in order to absorb heat from a low temperature medium and dump it into a high temperature medium. Instead of using efficiency, we are using a term called coefficient of performance. We show it with COP, and I'm going to put a subscript of R just to show that we are talking about a refrigeration cycle. And we define it as the desired output over the required input. Now for a refrigerator, what is our desired output and what is our required input? Now the whole purpose or goal of a refrigerator is to absorb heat from the low temperature medium or the fridge space, right? So our desired output is the amount of heat that we are getting from the refrigerator space. So the numerator is QL. How about the denominator? What is the required input of our refrigeration cycle here? It's the amount of power or work that it's consuming from the grid. So our required input is W net. So that's how you define the coefficient of performance for a refrigerator. It's QL over W net. Now, a first law analysis of a refrigerator cycle shows us that the W net is, again, QH minus QL. We can plug this back into our COP definition and get COP is QL over QH minus QL. We can further play with this equation and get 1 over QH over QL minus 1. So this is the coefficient of performance for a refrigerator. The other device that transfers heat from a low temperature medium to a high temperature one is called a heat pump. Now, refrigerators and heat pumps operate on the same cycle, but their goal is different. The goal of a fridge is to maintain the fridge space at a low temperature, and in order to do that, it absorbs the heat and then rejects that heat into a warmer space, like the kitchen air. The goal of a heat pump, on the other hand, is to maintain a heated space at a high temperature. And in order to do that, it absorbs the heat from a low temperature medium and dumps it into the high temperature space. Now, because the cycle of a heat pump and a refrigerator are exactly the same, we can use the coefficient of performance here again, but we need to modify it for the desired output. The desired output here is the QH, or the amount of heat that we are dumping into the hot space. So the COP of a heat pump, I'm going to put the HP in the subscript here to show that we are talking about a heat pump. Again, is the desired output over required input. This time it's QH over W net. Just a quick illustration for a heat pump. We have the high temperature source and the low temperature sink, and the heat pump in the middle absorbing QL and rejecting QH. I can play with this COP equation and get QH over QH minus QL, which again, if we continue to play with the equation, is 1 over 1 minus QL over QH. As I said before, heat pumps and refrigerators share the same cycle. Now in practice, sometimes heat pumps and refrigerators are the same devices as well, like air conditioning units. In summertime, they keep the temperature inside the building cool, whereas in winter, they keep the temperature high. Now for these devices, we can relate the coefficient of performance of the heat pump to the refrigerator. Okay. Now, if you compare the two coefficient of performances together, you can see that coefficient of performance of a heat pump is equal to the coefficient of performance of a refrigerator plus 1. Now, with that in mind, we can define the second law of thermodynamics, this time from a refrigeration cycle perspective. We call this new statement Clausius statement. So, the Clausius statement states that it is impossible to construct a device that operates in a cycle and produces no effect other than the transfer of heat from a lower temperature body to a higher temperature body. Now, both Kelven-Plank and Clausius statements are actually saying the same thing. One of them is looking at the second law with respect to heat engines, while the other one is looking at the second law from the perspective of refrigerators and heat pumps. Now, one thing that you need to pay attention to is that both statements are negative statements. So we cannot actually prove them mathematically, but no experiment so far has been able to contradict these two statements. Okay, now we can talk about reversible and irreversible processes. Now, a reversible process is a theoretical process that can be reversed without leaving any trace on the surroundings, meaning that both the system and the surroundings will return to their initial state when the process is reversed. Now, I said it's a theoretical process because no process in real life is totally reversible. Now, any process that is not reversible is an irreversible process. So the reversible process is the perfect ideal process, where the irreversible process is usually the actual process. Now you may ask, if the actual processes are always irreversible, why define the reversible process? The reason is that by defining a perfect and ideal process, we can study the system, we can study the cycle and the heat engine or the device or the machine better. And many of the actual processes, although irreversible, are very close to the reversible process. We can make the system in a way, we can make the cycle in a way that the actual irreversible processes are very close to the theoretical reversible ones. So analyzing and studying the reversible processes will eventually help us analyze and study the actual system or the actual cycle. Now let's talk about irreversibilities. There are different things that cause irreversibilities in a thermodynamic process. I'm going to list a few of them here. So the first one is friction. So friction is a very well-known cause of irreversibilities because it actually wastes energy. So let me give you an example. Let's say we have a surface that has friction, and then we have a box on top of it, and we are pulling this box this way. Now during the motion, when the box moves to reach the new position, some sort of energy is wasted because of the friction. So in this process, the box moves to second location and the surroundings gains work of friction. Now I'm going to move the box back to its original location to bring the system to its initial state. Okay? Now during the return process, the reverse process, again we are losing some work to friction. So when the box gets back to its initial position, the system has already lost work of friction twice, and the surroundings has gained work of friction twice. So neither the system nor the surroundings is in the first initial state. So this pulling and pushing is an irreversible one because of the friction. Now another factor is unrestrained expansion of a gas. Consider this piston and cylinder. Now during the process, this piston expands unrestrained to a new location, maybe here. So the system has reached the state 2. In order to reverse the process, we have to compress the piston to its initial location while transferring heat from the gas until it reaches its initial temperature. Now, if we do an energy analysis, it can easily be shown that the amount of Q that we need to take out of the gas is equal to the amount of work that is needed to compress the piston. So surroundings is doing the compression work while gaining some Q. If the surroundings during this cycle, this reversible process, wants to get to its initial state, the amount of Q that it gets should 100% transform into work, right? Because the surrounding is losing work, but it's gaining Q. The amount of Q is equal to the amount of work, but we know, based on the second law of thermodynamics, that the surrounding cannot convert 100% of the Q that it gets into the work. So the surrounding actually will not reach its initial state. And so the unrestrained expansion of a gas is an irreversible process. Another form of irreversibility is heat transfer. Consider a can of soda sitting in a room, and it is at 3 degrees Celsius, and the surroundings is the kitchen air at 20 degrees Celsius. Now we know that over time, Q is transferred from the hot kitchen air to the cold soda can until the soda can reaches the temperature of the air, 20 degrees Celsius. Now in the reverse process, if we want to take the soda can back to its initial state with a temperature of 3 degrees Celsius, we need to put it in a refrigerator, right? Because heat does not just flow from a hot space to a cold space. You need a refrigerator. Now, if we do that, if we put this soda in the refrigerator, the soda goes back to its initial state with a temperature of 3, but the surroundings has changed. And because of the refrigeration cycle, the surroundings has gained the Q that it provided to the soda can, plus the W net that was required for the refrigeration cycle to operate. So at the end of the reverse process, soda can, or our system, has returned to its initial state, but the surroundings, or the kitchen air, has gained a bit of work. So the surroundings did not go back to its initial state, and so the heat transfer is an irreversible process. Heat transfer can only occur when there is a temperature difference between a system and its surroundings. Therefore, it is physically impossible to have a reversible heat transfer process. But we can reduce the irreversibility of a heat transfer process if the temperature difference between the system and the surroundings approaches 0. Because if the temperature difference is very close to 0, then we don't need any refrigeration cycle to do the reverse heat transfer. And so the surroundings does not gain the additional power input or work input. Again, a small delta T, or a differential temperature difference, is completely theoretical and it's not practical. Now, based on the examples that we covered, we saw that there are certain processes, like the heat transfer, where the system would go back to its initial state while the surroundings will not. So if during the process the system itself, inside its boundaries, can go back to its initial state with no problem, that process is an internally reversible process. Now, a process is called externally reversible if no irreversibilities occur outside the system boundaries during the process. Now, a reversible process is a process that is both internally and externally reversible. So a heat engine that operates on reversible processes is a perfect and ideal heat engine. It is actually operating on an ideal cycle. And now a very famous ideal cycle is the Carnot cycle. Now a Carnot cycle has 4 different processes, all 4 of which are reversibles. This cycle will give us the upper limit or upper bound on the thermal efficiency. The first process is a reversible. I'm just going to put R instead of reversible. So a reversible isothermal expansion. So if I want to show the cycle on a PV diagram, from 1 to 2, the first process is an isothermal expansion. The second process is a reversible adiabatic expansion. A reversible adiabatic expansion, like this. Now from 3 to 4, we have a reversible isothermal compression. So from 3 to 4, we are on a constant temperature line. And then the final process is a reversible adiabatic compression. So 4 to 1 is like this. Now isothermal expansion is happening on the high temperature, and the isothermal compression is happening on the low temperature lines. So during the isothermal expansion, it is where the Q is introduced to our heat engine. So this is where QH comes in. And during the isothermal compression is where we are dumping the QL into the heat sink. Now remember, the area inside the curve of a cycle is the net work. So this area represents the net work produced by our Carnot cycle. So the Carnot cycle is the ideal reversible cycle operating between two heat reservoirs at T of L and T of H. Now there are two Carnot principles as well. Number one, it states that the efficiency of an irreversible heat engine is always less than the efficiency of a reversible one operating between the same two reservoirs. And principle 2 states that the efficiency of all reversible heat engines operating between the same two reservoirs are the same. So what it means is that if this is a high temperature heat source, and this is a low temperature heat sink, and then we have two heat engines, both on reversible cycles. Let's say one of them is Carnot, one of them is the other one. As I said, Carnot is one of the most famous reversible cycles. There are other reversible cycles out there. So if this is heat engine reversible number 1, and this is heat engine reversible number 2, then the thermal efficiency of reversible heat engine number 1 is equal to the efficiency of reversible heat engine number 2. Carnot heat engine is also a reversible heat engine. So this means that the efficiency of all these reversible cycles operating between these two heat reservoirs are equal to the efficiency of the Carnot. Now, can we find the Carnot cycle efficiency? This brings us to our next topic, efficiency of Carnot cycles. Now, for a Carnot cycle operating between a high temperature heat source and a low temperature heat sink, we know that the efficiency, thermal efficiency of a heat engine is 1 minus QL over QH. Now, for a reversible cycle, for a reversible heat engine or a Carnot heat engine, we can replace the ratio of QL over QH with TL over TH in Kelvin units. So the thermal efficiency of a reversible cycle, namely the Carnot cycle, is 1 minus TL over TH. Now the math behind how QL over QH transforms to TL over TH is a bit complicated, and I decided to not include it in this video because I wanted to keep things easy and practical. But remember that for a reversible heat engine, the ratio of QL over QH is equal to the ratio of temperature of the sink to the temperature of the source, given that the temperatures are in Kelvin unit. Now we can define a refrigeration cycle or a heat pump cycle that operates on reversible processes, just like a heat engine. Okay, so we have an ideal refrigerator and an ideal heat pump. We call them the Carnot. We call them the reverse Carnot cycle or the Carnot refrigerator. So remember that the coefficient of performance for a refrigerator was 1 over QH over QL minus 1, right? And the coefficient of performance for a heat pump was 1 over 1 minus QL over QH. Now, for reversible refrigerator and heat pump, or for a Carnot refrigerator and heat pump, we can change the ratio of QH to QL to TH over TL. QH over QL is TH over TL. So coefficient of performance for a refrigerator turns into 1 over TH over TL minus 1. And the coefficient of performance for a heat pump turns into 1 over 1 minus TL over TH. Now these are for reversible ideal cycles. Now for heat engines, if the efficiency, the thermal efficiency, is smaller than the efficiency of the Carnot cycle, then it means that we are dealing with an irreversible heat engine. If the thermal efficiency is equal to the Carnot efficiency, we are dealing with a reversible ideal heat engine. And if the thermal efficiency is greater than the Carnot efficiency, we are dealing with an impossible heat engine. Same thing goes for the coefficient of performance. So for the refrigerators and heat pumps, if the COP is smaller than the COP of the Carnot fridge or Carnot heat pump, we're dealing with an irreversible cycle. If the coefficient of performance is equal to the COP of Carnot, we are dealing with a reversible ideal cycle. And if coefficient of performance is greater than the Carnot COP, we are dealing with an impossible refrigerator. Thank you for staying to the end of yet another video. If you find this video helpful, please give it a like, as it greatly helps the channel. Also, please consider subscribing for more science and engineering content. Thanks again, and see you in another video.